Hello and welcome to the next episode of our computer build. Now, where we left it last time is we had these resistors here which were permanently programming one instruction into the processor, and that instruction was EA, which is the instruction to do nothing. Well, that's not going to be too much good, is it, if we want to program a whole bunch of different instructions. So what we're going to do now is we're going to have a look at this. This is a ROM chip. Specifically, it is an Atmel AT28C256 ROM chip. Now, it's worth asking what a ROM chip is, and the best way to describe it is to have a look, as always, at the datasheet. So let's go and do that. Okay, so here we are at the datasheet, and this is the particular package we've got. So let's have a look and see. Now then, we have got, firstly, IO 0, 1, 2, 3, 4, 5, 6, 7. So these 8 are the data pins. Okay, and then we've also got ourselves 15 address pins. And they're in a really daft order, but you can see 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 and 14. So the way that this ROM chip works is if you throw an address at it from one of these 15 lines, then it will spit out whatever number it has got stored at that address out of the data lines. So if you remember from our 6502 processor, it's going to look at address, let's say 0, and it will get a piece of data from the ROM. When it'll do that, then it'll look at address 1 and then get the next piece of data, and then address 2 and get the next piece of data. So this is precisely what we want. Instead of having to program it one piece of data at a time with resistors, we can just store up to 32,000 different instructions and just recall them in as and when we want them, which is great. There are a few other pins that we need to talk about. We've got our power supply here and our ground there, as you would expect. And then there's 3 other chips, 3 other pins, my apologies. And we've got chip enable, CE, and that's bar. So that is active when it's low. So the chip only works if this is low. We've got output enable, which the chip can work, but it won't output anything. That's not useful for our purposes. And that is only active when it's low, so we need to tie that low. And then we've got write enable. Now, we don't want to write to this chip. I mean, we do, but not with our computer. We're going to use a different means to do that. So again, we want to disable this, so that needs to be tied high. Now then, let's go and have a look at a sort of little diagram I've drawn. We've got our chip here, and we've got our 6502 processor here, and these 16 lines, numbered from 0 to 15, represent the 16 address lines that the 6502 processor can ask for. But of course, we've only got 15 address pins on our ROM chip, and that's because the ROM chip does not have 64,000 addresses like the processor does. It only has 32,000. So how are we going to deal with that? Well, one thing we could do is we could just ignore it and not plug it into anything, and that's fine. Let's have a look and see what would happen under those circumstances. So let's say the processor sends out 0, 0, 0, 0 hex. So here we are, all noughts. Well, that's fine. It will find address 0, and it will go on counting up and finding addresses all the way up to 0, 1, 1, 1, 1, 1, 1, 1, 1, which is 7 FFF. So far, so good. We can find all of the addresses on the ROM chip, no problems. But what happens on the very next address? 8,000. Well, it's 1 and then all zeros, that's address 8,000. But of course, this chip's not seeing this particular byte, so it just goes back to the beginning and starts from 0 all over again until we get to FFFF, which is all ones. So if we just connected up the 14 pins to the first 14 addresses, we would see this ROM chip twice in address space, once from 0 to 7 FFF and once from 8000 to FFFF. Now, maybe that's fine, but there's 2 problems with that. One is that it's kind of wasteful of address spaces to have the same thing twice. And then secondly, it takes up every single last address that this processor has got, and we need to use some of those addresses for other things like, video or input output or attaching a keyboard or something like that. So what can we do about it? Well, one of the things we could do is we could attach this pin to our chip enable bar. So this is only active when it's low. So going back to the beginning, when it's low, we start with address 0000, and it counts all the way up to address 7FFF, all fine. And then on the very next address, 8000, this goes high, and that disables the chip enable, and then this ROM chip doesn't respond anymore, so we've got all these addresses that we can use from 8000 all the way up to FFFF for other things. Perfect. So let's do that. Now, there is one caveat, and to talk about that, we're going to have to go back to our data sheets. Now, if we go back to the data sheet of the actual processor, let's go back and have a look what it says about the reset pin. My apologies. Most importantly, it says there'll be a reset sequence lasting 7 clock cycles, which we know, and the program counter is loaded from locations FFFC for the low byte and FFFD for the high byte. This is the start location for program control. So going back to our diagram, we have ourselves a bit of a problem. It's going to look for where it wants to start the program in the top half of the address space. It's asking it up here, FFFC and FFFD. And with this particular setup, it's just shouting that into the void. So what can we do? Well, absolutely there is something we can do. Okay, we can put in an inverter. We know we have chips that have inverters, so that what that then does is it inverts this signal. So now, at address 0, this signal is now, this is low, it becomes high, and it switches the chip off. And the chip is off for the whole bottom half of the address space, but then switches on for the top half of the address space, which includes FFFC and FFFD. So that means we can get ourselves a reset vector. So the only slight irritation with this is, one, we've got to use an extra logic chip. Well, that's fine. We will find ourselves using more and more and more complicated, this is called address decode logic, to make sure that the right addresses go to the right chip and the right signals come back. And the other slight issue is that this ROM chip is going to count from 0000 up to 7FFF, but we're going to address it from 8000 up to FFFF. And that's not a problem. We're just going to add 8 to all of the bytes on here to tell the 6502 what to address. So if the 6502 wants to address 1000 in the ROM, it needs to address 9000. And if it wants to address 2000, it needs to address A1000. If it wants to address 3000, we need to go to B1000, and so on and so forth. So that's fine. Now, I guess we'd better get the chip installed in the computer. So let's do that. Okay, so here we are back at the computer. Now you'll see I've actually connected it all up already. That's because connecting up this many wires on camera is just would be unbelievably tedious. But let's just make sure we understand what's going on. So this is the ROM chip, and this is a 74LS04 chip, which is full of inverters. So we've got our 8 data lines going in that direction, and we've got our 16 address lines going in this direction. Do you remember they're in a daft order? We've got power going to our 74 LS04 chip. We've got power going to the ROM chip. We've also got the write enable tied high. That's active low, so that won't work. And we've got the output enable tied low, which is active high, so it will. And we've got the chip enable, which is this one, tied to our inverter and off to address 15, which is the 16th address, given that we start counting at 0. So with a bit of luck, this should work. Now, before we do too much, the problem is that we've got ourselves an empty ROM chip. It hasn't got anything on it. So we've got to put something on this ROM chip that our computer will recognise, and some code that it can run. And that's going to be the topic of the next video. which I will see you at next time. Goodbye.